so hello everyone. I'm Johan, and I'm co-leading the vLLM project with the team at UC Berkeley.
Hello, my name is Cade. I work at Anyscale, and I'm a contributor to vLLM. To start out our talk, we want to understand a little bit about how much experience you have with vLLM. So if I could ask you to raise your hand if you've contributed to vLLM. Expected maybe a few people. How about have deployed vLLM? Okay. And how about have heard of vLLM? Okay, good.
Okay, good. Yeah, that's good. Okay, so today we are more than happy to share some of our recent updates on the project and on behalf of the amazing vLLM community from UC Berkeley, Anyscale, and also including companies like Neuromagic, IBM, Roblox, and many, many more other open source contributors. So for this talk, I will first start with a short introduction of our project, and then I will go through an overview of our features, what we have in vLLM, and then I will talk very briefly about our roadmap, and then in the end, Kate will dive deep into two of the very important recent updates we made for the project, which is two features. One is chunk prefill, and one is spec decode. And yeah, let's get started. So let's start with the introduction. And yeah, obviously we are in the era of large language models. LLM have shown remarkable capabilities in a wide variety of tasks, from chatting, programming, to search. And some of these applications, such as ChatGPT and GitHub Copilot, are already changing our lives. And not surprisingly, a key part of these applications is the systems that serve these LLMs using GPUs. But however, we noticed that serving LLMs is surprisingly slow and expensive. And for example, for systems before vLLM, a single GPU can only manage to serve less than 1 request per second for moderate-sized models and inputs. This means that you need a ton of GPUs if you actually build a production-scale services using LLMs. And indeed, the high cost of serving LLMs have been a major challenge for everyone in the field. And even hyperscalers like Microsoft have struggled for securing enough GPUs for their LLM power services. And this challenge motivated the vLLM project. And we started the vLLM project to build the fastest and easiest to use open source LLM inference engine. And back then, at the time we started the project, all open source solutions were either slow or very difficult to use. So we decided to make one by ourselves. And while building up vLLM from scratch, we discovered that how to manage the KV cache memory is the key to the serving performance. And the KV cache is a unique component in LLM serving that keeps the states for the incremental decoding. And because KV cache is pretty new, it wasn't efficiently managed by the existing systems. So to address this problem, we came up with a new technique called page attention, which is a new attention algorithm that operates on blocks of KV cache. So page attention enabled highly flexible memory management. We could manage the KV cache like the virtual memory in operating systems, achieving efficient and elegant space sharing between the multiple requests. And we have observed huge performance improvements and decided to open source to share the results. And fortunately, we got a lot of traction from the beginning, and vLLM has continued to grow rapidly with the help of community. And today, vLLM is the most popular open source project in the field of LLM serving. So vLLM has a pretty simple and nice end user API. So first, vLLM has a Python class, LLM class, which is a Python interface for offline batched inference. So you can simply create an LLM object with the model name, and then call the generate method to efficiently run inference on a batch of requests or a whole data set. And you can also start vLLM as an OpenAI API compatible server with a single command. And then you can reuse the OpenAI client by simply replacing the URL. So with these nice APIs, vLLM provides a full-featured LLM inference engine with a wide range of model support, diverse hardware backend, and extensive state-of-the-art inference optimizations beyond the original idea of page attention. And we'll dive into these features in a moment. And vLLM is actively developed by more than 390 contributors from all over the world. And also, like vLLM has been integrated in popular open source projects such as Chatbot Arena, and has been deployed in many companies, including Databricks, where we're giving the talk today. And most noticeably, vLLM has become the default LLM serving engine on many clouds, including AWS SageMaker, and also Azure like AI Studio, and also Google Cloud's Vertex AI service, or like Oracle Cloud's like OCI generative AI service, and also on RunPod. And also we are featured at the AMD MI300X launching event. So to give you a more detailed view about our user profiles, so we have like in general 4 kinds of different users. The first is as we just discussed, is the model as a service providers, including all kinds of cloud companies. And also there are many AI infra companies like Anyscale and Neuromagic are using using vLLM. And also we have many model developers who use vLLM to serve their model and also contribute to vLLM, contribute back their model. And also we have AI-enabled products like Roblox and LinkedIn, which integrate vLLM into their productional services. And among all these users, many of them actually contributed back to vLLM. And all the highlighted companies here, they have contributed back to the vLLM repo. And one highlight I would like to make is from hardware vendors. We have all different kinds of hardware vendors, like from AMD, Intel to Google TPU and AWS Inference. They want to add their hardware support into vLLM, and they are intensively contribute their code for the support to their hardware to vLLM. And the engagement of the community is actually really growing over time. So from time to time, the new commits come more and more from outside of the Berkeley. And right now, actually, most of the new commits are from outside of the Berkeley. And also beyond the contributor community, we would like also to thank many companies on this page for sponsoring the compute need to run the CI/CD and benchmark, and also the daily development of the vLLM project. And next, that's all for the vLLM introduction, and I will give a feature overview of the vLLM project. And let's first start with the extensive model support. So right now, vLLM has the community support of more than 30 different types of model architectures, which covers almost all of the popular LLMs. And we have continued to support more and more models out of the box. And it's noteworthy that many models, and these marked as blue, are added by model vendors. So you can trust this implementation. And we have also added support for many exciting new architectures beyond like just simple autoregressive language models. So such as like embedding models like E5 Mistral, and also state space model Jamba. And also one thing is that we recently added the out-of-tree model support. So you can add your proprietary model to vLLM without changing the code base of vLLM. And as we mentioned before, so in terms of the front end, we support the OpenAI API server with the embedding model and batching format. So you can use just one single command to start an OpenAI API server, and it covers most of the function of the like as if you are using the OpenAI API service, and you can just replace one line URL to switch from the OpenAI service to your own LLM with vLLM. And one thing I would like to highlight is that we also support vision input right now. So vLLM can serve multimodality models, and you can serve a mixture. You can send a mixture of image and text, which opens a new possibility for like different use cases. Yeah, and for hardware support, we already have mainstream CPU and GPU supported, and together with like new hardwares like AWS Neural. And actually, just in this week, we added support for Google TPU, and also Intel Gaudi and Intel GPU support is also on the way. So please rest assured that you can get the top-tier user experience because they are dedicated engineers from hardware vendors working on the integration. And also, like in this talk, I would like to highlight several key features that we are working on in the past months. They are ready for testing and production, and most of them will be on by default in the upcoming releases. And I will talk about, I will mainly talk about quantization and prefix caching and guided decoding here, and Kate will dive more detail into trunk prefill and speculative decoding. So first, about quantization support. So as the early days of vLLM, we actually have spent quite a lot of time, like refactor vLLM to make it able to support all kinds of different quantization methods. So right now, we support GPTQ, AWQ, and squeeze LLM. These are all different kinds of weight-only quantization methods, and also we support FP8 KV cache. And also, we recently are adding support for full FP8 execution, given that there is a transformer engine on H100, which can fully makes the FP8 performance very, very good. So right now, like we are actively adding support for FP8 support. Right now, we have already. So you can see, you can see that with the FP8 quantization, that it can be reduce the latency to half when the request rate is high. And also, like another feature we would like to highlight here is automatic prefix caching. So many chatbots have very long system prompts to shape their behavior, and this system prompt can be even longer than the question and the answer. So for example, ChatGPT is reported to have more than 1,000 tokens in its system prompt. And the characteristics of the system prompt is that it is shared by all users, so we can reuse the computation here. And also, the prompt sharing also occurs in multi-round conversations, so where the previous round will be exactly a prefix of the next round. So in both cases, we can identify the part of the prefix automatically and caches the computation accordingly. And this automatic prefix caching is working now in vLLM. And so more specifically, so all of these prefixes will be automatically cached in vLLM's page attention, and new requests will be directly use the cached prefix without recomputation. And then when we are running out of memory, and like because it's being filled with all kinds of different caches, we'll evict the caches with the LRU order. And this has been already implemented and merged into vLLM main branch, so you can directly enable this feature by passing in this feature flag. And also now we support guided decoding through the library outlines. So you can specify, okay, I want to output a JSON format for my LLM, and we can force the LLM to output the JSON format. And also in our OpenAI API server, we have supported function calling, which uses the guided decoding feature, and can also make sure like this part of the server also is compatible with OpenAI's API server. And besides of all these kind of features, we are continuously doing more and more different kinds of optimizations for performance, so which includes like integrating with state-of-the-art kernels and also optimizing the kernel by ourselves, and also improving the communication performance, and also have better system architecture design within the vLLM to make the vLLM faster. So first, we have been integrated with state-of-the-art CUDA kernels for attention computation and decoding, such as flash attention and flash infer. This shows significant speed up on high-end GPUs. And also, as model grows rapidly in size, we often need to do multi-GPU inference, and which is very difficult to configure and use. So vLLM takes all of the trouble, and we provide a debugging guide and select the best version of the libraries with the proper flags. And we also have a dedicated all-reduced kernel for high-end machines with NVLink and P2P access capability. So in short, vLLM will handle the communication for you, and we will find the best way to make your multi-GPU inference fast. And also, yeah, one last thing before I dive into our future roadmap. So one thing is that our system is right now have a very very well tested. Every commit it will go through a CI/CD process. So and we have an intensive test to make sure our software is delivering both correct answers and also delivering correct answers fast. So yeah, and I think like we are trying our best to make vLLM real production scale, production ready software. And next, I will spend a couple of minutes to talk about what we are going to do in the upcoming quarter. So first, we'll have more and more model support. So in general, we'll improve the performance. We'll try to add more vision language models, and we'll add support for encoder-decoder models, and we will try to add support for more different kinds of state space models like Jamba. And also, in terms of hardware support, we'll make our FP8 performance better, and we'll keep optimizing our FP8 performance, and we're also optimizing our performance on MI300X, and we're also focusing on landing on more different hardwares, including TPU and Intel GPUs. And also to make our engine more production ready, I think in the near future, we will try to make the features we recently implemented more and more robust and try to make them on by default. This includes trunk prefill and automatic prefix caching. And because the models are getting larger and larger, for example, the largest Llama 3 model, which hasn't been released, will become 400 billion parameters. This means that cross-node inference will become a necessity in the near future. So we'll also spend time on implementing pipeline parallelism in vLLM. And also in terms of performance, as we just mentioned, we'll work on have better FPA support, and also improve our performance in speculative decoding, which Kate will dive more into the detail. And also we'll work on more researchy features like KV cache swapping. And also, in terms of making vLLM a better software in general, we will try to keep optimizing the existing overhead within vLLM. For example, make the scheduler more efficient. And also, we will try to integrate with Torch Compile so that for every new model, we can have a very good performance with the compiler. And in the end, most importantly, vLLM is an open source project, so we would like to continue our support and engagement with the open source community. So we will make sure to have a better benchmark, so we can always make sure our performance is good. Also, we'll keep improving our CI performance and also code quality. So to summary, let me re-emphasize, our goal is to build the fastest and easiest to use open source LLM inference and serving engine, and we are confident that we are on the right track. And next, I will hand over to Kate, who will present a deep dive on trunk prefill and speculative decoding.
All right, great. Thanks for the intro and overview of vLLM. So I'm going to go over two features in vLLM. One is called trunk prefill, which we'll talk about now, and another is called speculative decoding. These features provide very large impact in terms of performance, and that's why we're highlighting them here. So trunk prefill, here is a chart which shows the impact of trunk prefill. On the x-axis, we have QPS, queries per second, to your model replica. And then on the y-axis, we have average request latency. And we can see that vLLM without trunk prefill, this gray bar, the latency to complete each request goes up as the QPS goes up. And trunk prefill at high QPS regimes provides a 2x reduction in latency. So I'm going to give a brief introduction of how this optimization works. So a quick reminder for how LLMs work. LLMs are autoregressive. So when you give a prompt to ChatGPT or Llama or whatever LLM you have, the LLM must first ingest this prompt into its understanding. We call this the prefill phase. And in this diagram, these are the yellow blocks. This is the query you give to your LLM. And then the LLM will generate token by token the answers to your question, to your prompts. And so this here is represented by the blue boxes. And we add one at a time. And eventually, the LLM will decide when it has completed its generation. And here, this is represented by a red token. We call this an end of sequence token. And so the process here is the LLM takes your prompt, ingests it, and then one by one produces tokens until it completes the answer. This is how all autoregressive LLMs work. Now, before vLLM came out, a few years ago, we had a technique called static batching. So we all know that GPUs, with all of their compute and matrix multiplies, are necessary for serving LLMs. But to actually get the worth out of a GPU, you need to do batching. Otherwise, if you just do one request at a time on a GPU, you spend a lot of money. So the technology of old, around 2 years ago, is something called static batching. And here we have 4 sequences. So S1, S2, S3, S4. And we prefill them all onto the GPU. So our batch size is 4. And then just like in the diagram before, we're going to incrementally add tokens and query the LLM to complete the answers for these 4 requests. And as you'll see here, each sequence will finish at a different time. Maybe one user is asking, what is 1 plus 1? And the other user is asking to summarize a Wikipedia article. Now, this technology got us to where we are today, but it's very inefficient. Because in the time that it takes to complete the worst sequence, the longest sequence, the GPU is idle for the other sequences. And this is represented here by the white boxes on the right side. So page attention, which was innovated by Johan and a few others, combines continuous batching and solves this problem. So here we start with the same starting conditions, where we have these 4 sequences, and they're each adding tokens. And they all finish at the same time in the other diagram. But instead of wasting the GPU time, where these white boxes were, we begin to immediately put on new sequences in its space. So here we have sequence 6, sequence 5, and sequence 7. And what this allows us to do is achieve really high GPU utilization. And this is what made vLLM famous and got some of the amazing performance numbers. And this is the standard for many serving frameworks and LLMs today. So now we understand continuous batching. Let's go back to chunk prefill. So chunk prefill is an optimization over the naive continuous batching. So this diagram shows exactly what I just showed you. And we can see here that the blues are the decode. Now decode means we're emitting a single token. But when a new request comes in, for us to put it onto the GPU, we need to ingest that into the LLM, or prefill it. And these are represented here by the green boxes. And if you look at request 1 at the very top, it's decoding, emitting tokens to the user, but a new request comes in, and for the duration it takes to ingest that new request, the user behind request 1 doesn't get any new tokens. There's a gap, they perceive latency. It's a suboptimal user experience. Now for 1 or 2 requests, this doesn't matter that much. But in this diagram, as we scale to 4 requests, you can see that request 1, maybe more than half the time is spent waiting instead of generating tokens. As a service provider, this is a really bad trade-off for your users. It makes serving it cheap for you, but gives them a suboptimal experience. So now we'll come to chunk prefill. Chunk prefill is an optimization over this that allows you to blend the prefill green boxes and the decode blue boxes. So here on the left, we have the same diagram we just saw. And here on the right, we have chunk prefill. And the first thing I want to highlight is request 1 sees a continuous stream of tokens. There's never an interruption or a pause for other users. And the new users, requests 2, 3, and 4, they also get to their tokens very quickly because the prefill happens in conjunction. It's mixed with the decode batch. And this is how GPU service providers serving LLMs using chunk prefill are able to get the best of both worlds. Your new users don't have to wait, and your existing users can still get their tokens very quickly. There's a lot more detail here. The code is open source, and there's a lot more to optimize. But I just want to highlight the results that we see. Again, at QPS 8, when you have a lot of new requests coming in per second, this produces a 2x latency reduction. And this is a great example of research quality work that goes into the framework that Johan et al. Have built. So now I'll talk about one more optimization that is in vLLM. And this is called speculative decoding. Speculative decoding is a pretty popular topic. Maybe you've heard Andrej Karpathy speak about it. And I'll first give an overview of what is speculative decoding. So I recommend you go read Andrej Karpathy's tweet about speculative decoding. You can Google it. It's 1 or 2 on the Google results. The TLDR here is speculative decoding allows us to accelerate the speed at which we emit tokens from an LLM. Now, there's something called memory boundedness. And this is when your GPU is spending more time loading weights than it is doing computation. And when our GPUs are memory bound, we're actually wasting some of the flops on the GPU. It's sitting there idle. Speculative decoding is a trick that allows us to use those flops to emit more than one token per iteration. Now, how does this trick work? First, we have to observe that not all parameters are necessary for every token. So if you ask, like Llama 3 70B, what is the capital of California? You probably don't need every one of those 70 billion parameters to answer that question. You could probably use a 1 billion parameter model or even smaller. So the key idea of speculative decoding is we try to use some other technique to guess what the large model will say. Then we use the large model to get the probabilities of those predictions, of those guesses, using those spare flops that I talked about. And if our guesses are correct and the large model gives a high probability to the guesses, then we can emit those guesses as tokens that are verified by the large model. And so fundamentally what this means is if our speculator, our predictions are good, we can emit 2, 3, 5, even more tokens for one iteration of the large model. So just to give a cool diagram, this is from a paper called Accelerating LLM Inference with Staged Speculative Decoding. The prompt here is in gray, and this is a coding completion question. And the blue come from a very small LLM, like 100 million parameters. The red come from the full size LLM, so like 70 billion parameters. And the green come from a very tiny n-gram model, like CPU only, not even LLM. And what we see here is that instead of spending all of our time waiting for the red LLM to generate all of this content, we can actually use these much smaller LLMs to emit these tokens. And this is precisely because the large model accepts them. The probability of that token is high. This is a really cool demo that shows which tokens, the easier tokens that are accelerated by speculative decoding. Now, how do we evaluate the speed up? There's a lot of math here, and if you're interested, I recommend checking out this paper out of DeepMind. In particular, this diagram highlights a trade-off between alpha is how accurate your draft model is, and then the y-axis here is the speed up. And it also shows something for the cost of verification. So if you're interested in that, I recommend you go read it or come talk to me afterward. I like to simplify things in vLLM, and we can simplify it as the intertoken latency, which is the time per token, comes down to the step time divided by the number of tokens per step. So in vanilla vLLM, the step time is maybe 30 milliseconds. And for every decode step, you'll get one new token. So this means that we have 30 milliseconds per token. Now, with speculative decoding, we add some overheads with this draft model, with this verification. So maybe it takes 40 milliseconds for a single step. But on average, we can get 2.5 tokens. On average, 2.5 tokens are guessed correctly by the small model. And what this means is that we get one token per 16 milliseconds. And so there's a lot of complexity inside vLLM that's managed, but from the user perspective, we went from 30 milliseconds per token to 16 milliseconds per token. And how this is managed depends on things like how aligned your proposal method are. If it's not good at producing guesses, then you won't get this kind of speed up. And also, of course, is how long does it take to run your proposal method, score it, and verify it. One last background information on speculative decoding is losslessness. So if you have a really poor proposer, does it affect the output of your large model? Because if we want the quality of the large model, we don't want to compromise on that. Another paper here, it's also out of DeepMind, gives a proof of losslessness if you use a technique called rejection sampling. And basically what this technique is it will reject more guesses of the draft model, but it provides a guarantee that when you sample from this modified distribution of speculative decoding, you're guaranteed for the distribution to converge to the distribution of the target model. So yeah, a lot of technical jargon there, but at the high level, what this means is that mathematically, there's no difference between the target model and this modified distribution via speculative decoding. These diagrams here show in vLLM how this math plays out. So on the left side, we see the target distribution, which is blue, and the draft, which is orange. They vary because the draft is not as powerful as the blue. And then on the right, the target is now orange, and then blue is speculative decoding. And we see that it converges towards the target model. And this is, shows how the quality is the same with the target model and with speculative decoding. So that's background on speculative decoding, and I'll talk about how it fits into vLLM. So the current status is there's a framework built into vLLM, and the framework is completely merged and feature complete. In fact, there's even correctness tests, so contributors can add to it and even improve the performance. We support a draft model, like a very small 100 million parameter model. We support Ngram. There's work ongoing to support Medusa and other advanced techniques like IBM's MLP Speculator. And there's also other features that make it really easy to use, such as skipping speculation for some sequences and some other research, which I'll talk about in a second. And in terms of using this in production, you can get latency reductions with what's merged into master today. But there are some more performance optimizations that we need to do to get to the target 2x latency reduction. If you're interested in helping or following along, check out this GitHub issue. And just to show ease of use, as Johan mentioned, ease of use is very important for vLLM. We create an LLM instance, we have our prompts, and we simply specify to LLM that we have a speculative model and the number of speculative tokens. And so super, super simple. And for the other speculative types, like for Ngrams, it's a different proposer type, which is very cheap. You can just replace it, your speculative model, with Ngrams. And then I will skip over this. This is basically how this is implemented inside vLLM. This is oriented more towards contributors. The key idea here is there's 3 stages: proposing, scoring, and verifying. We accept or reject tokens. And just to go a little bit further into these 3 stages, we can actually replace them with many different components. So proposing is the first stage, and we can use a draft model, we can use Medusa, we can use different things. Scoring is your target model that you care about. And then verification, as I said earlier, was lossless. However, you can also swap out your verification routine with something that's lossy and trade off some quality to get even more speed up. And then because we've built a framework in vLLM, it also allows us to further improve the state of the art on speculative decoding. So there is a PhD at Berkeley, her name is Lily Liu, and she has done work on something called dynamic speculative decoding. And I won't get too much into the details here, but the key observation is that if QPS goes up and you have to spend more and more time on the computation for verifying all of these speculations, you actually end up increasing latency. So beyond a certain point, your latency goes up, which is not what we want. And we can see here with the green boxes, this is 5 speculative tokens per sequence. And as we increase the QPS on the x-axis, the speed up goes down even below 1.0 at some point. And basically, Lily's work, you can go check out this RFC on the GitHub repo. I'm going to skip to a slide that shows the results. Here we have blue, which is without speculative decoding. And then this is based off Medusa results, which is one of the more aggressive speculative types. And we see that it quickly, as the request rate goes up, suffers and eventually becomes worse than no speculative decoding. With Lily's work that's implemented and in progress in vLLM, we can actually adjust the aggressivity of the speculation so that the latency is never worse than without speculative decoding. This is fantastic work, and if you're interested, I highly recommend checking it out and working on it. These are some results that Lily ran with a very basic dynamic speculative policy. And it shows that the latency reduction we get is never worse than without speculative decoding. More results here. We can share the slides on dynamic speculative decoding. And as I said, there are open source contributors which are adding different speculator types. And in fact, this is an open research area. There's still new papers that come out with improvements on speculative decoding. And it's our hope that these get contributed to vLLM so that users can benefit from the ease of use of these new types. Lastly, if you're interested in contributing to speculative decoding in vLLM, here's a list of ideas that I wrote out. Some of these are engineering heavy, like retrieval acceleration, where you'll use a database like a RAG store to produce your speculations. Other ones combine like chunk prefill, spec-decode, things like this. However, if you're like a modeler, you can do things like using a multi-LoRa draft model and have each LoRa specified to a certain domain. There's a lot of potential work here that's very interesting, and we hope that vLLM can provide the foundation for that. This concludes my deep dives, and it concludes our talk. We'd like to thank you guys for coming, and we'd like to highlight that Ray Summit, which is hosted by Anyscale, has opened a track for vLLM. So call for proposals is open. If you're a user or have some cool technique that you want to use in vLLM, please apply. Thank you.